a group of people that had Argus, active Argus projects. So I would go through some of the details they needed for their particular projects. I don't think we have that here right now. Our team, Group 4, did a little bit of Argus observations. So we have a high frequency, we have the Mustang receiver that can do continuum work. For spectral line work, we use the Argus array. It's a 16 element feed horn array. And I will just share my screen here. There's an Argus web page. You get to it by just going to the normal NRA, well, the www.gb.nrao.edu. So we still have NRAO in these pages. It's the same page you can go to get Vegas. I don't know if you know about the Vegas pages to get all the modes. But you can go Argus. And so we have information here on this web page for submitting proposals, including examples on doing time estimates, walking through the sensitivity calculator and the mapping calculator. There's some basic information, its frequency range, its receiver noise, and some of the basic stats. With the documentation for this instrument is linked here off the page. So there's an observing presentation, it's the PowerPoint. That's what I typically can step through, and we'll go through a little bit of that, and I'm just going to hit some of the high points or areas in which haven't been already covered. There's an observing chapter in the observing guide. Oh, this is an old web page that's just general. We have the SPIA paper. Matt Seath was a graduate student. He's from Stanford, who put the instrument together. He came to the observatory and worked with one of our engineers and put it together, tested it in the lab, and then I commissioned it on the telescope back in 2016. How we do calibration of this instruments in this GBT memo 302. If you don't know how people do millimeter calibration, this is sort of, you could go to that. It has a basic background on all the different temperature scales. I'm just scrolling through it. Actually, am I sharing my screen? Can you guys see this?
Yes.
Might not be.
Yes, we can.
Okay, yeah. I don't see the box around my window. So, okay, it's over on the other side, sorry. No, it's, normally I could see the little Zoom box around the window that show it's being shared. Anyway, all the equations are in here and the methods are in here. I'm not gonna obviously go through that. And the results basically in terms of what we got and found in terms of the aperture efficiency, the beam efficiency. So you move to higher and higher frequency, your beam gets smaller, your aperture efficiency goes down exponentially with the Ruse equation due to the surface. So at the higher frequency, it's very important to get your pointing, your focus, and your surface done properly, or you'll be at very, very low efficiency. So this is when we are doing things well. So if you're not doing things well, if you have a bad surface, all these curves can drop quite significantly, and you won't see much if you're looking at a point source. If you're looking at a very extended region, it really doesn't matter too much because you're just seeing out in the forward direction on the sky. So that's all sort of discussed in that calibration memo. So I can go through a little aspects of what's different about Argus in comparison to our other receivers. So this is just, but first, where to find information about Argus, this web page that I was just showing you. We have example observing scripts in this Home Astro Util Projects Argus OBS, and the example reduction scripts under PRO for Pro, their IDL or Gbt Idl scripts. Argus, like the W-band receiver, has no noise diodes, so the regular Gbt Idl scripts don't work. You need noise diodes. It tries to for that to work, as well as our pipeline. Our default pipeline requires noise diodes. One point they were going to implement things within the pipeline not to need noise diodes, but that project sort of ran out and they never got around to doing that. But I do have scripts available for that can reduce all different modes of data that you would take with Argus. They're not user friendly. They're not user unfriendly. I wrote the scripts, but they're not professionally written by a programmer. They're just written by an astronomer who writes scripts to, for people to reduce their data. Other staff members have scripts too. Larry wrote a script to parallelize, to do some of the processing in parallel to speed it up. But you need to talk to your friends of your projects if you're having issues or need assistance with data reduction. I'm not going to go through this stuff. This is just background material which we've already seen. It's a big dish. We have an active surface. We use the Zernikeys to correct the Zernike gravity model. That was actually an important thing that's written up in a project note that Ron and I did back a few years ago. And you saw the improvement over time. Here is our first few observations with Argus. We did first light with Argus even before we had a cow wheel, or I mean the vane. So, and we only had part of the array. That was back in March of 2016. And then we took a CO spectrum a month later, and then we took a map. That was the first map. When we got all 16 beams, we took a map of DR21, but we still didn't have a vane to calibrate at that point. But anyway, I'm going to show you our beams pretty good. The block diagram, we'll mention this, that point out a couple differences with Argus with respect to all the other receivers. Here's a pretty picture of the instrument. I guess we should put something to scale, but these are 3mm feed horns. You can see it's a 4x4 configuration basically. And this was just a prototype project. The idea here was to prove that you could build these modules in a small enough space in which you could expand upon it. So everything's underneath the feed horn, so you can pack these in together. And all this is in a cryostat. It's not open like this. This is just an open picture of the cryostat. So we take our LO, we actually copy it 16 times to go to our 16 different channels here. We have this thing from the CSO, a hand-me-down that came from the CSO to Caltech to Stanford to Green Bank, basically on loan officially. Hopefully nobody at Caltech knows about it, so don't tell them that we have it still. But it's just surplus. And it does a filter to clean the, and it only lets a 50 megahertz Y signal come out of the LO. And that's different in the sense that if you switch frequencies a lot with Argus, go from one end of the band to the other, it takes a while for this piece of hardware to stabilize. So if you're doing lots of different lines and sources, I would arrange, it's better to actually arrange your science based by lines and clump those observations together and bounce around on the sky, then to arrange it by source and bounce around in frequency, just from a practical standpoint. And it uses an IQ mixing scheme, which flips the phases around. This is different than to do sideband rejection, and there's a sideband. So you can do either upper or lower sideband, and we typically use lower sideband for everything except the highest end of the band, then we use upper sideband. The footprint on the sky looks like this. So it is just 4x4. Ironically, we thought we installed it the other way in terms of elevation, but when we went on the sky, this is actually what the different pixels see. There's some technical points with Argus. Beams 9 to 16 can only be, they're the only ones that can be connected to the DCR for pointing and focus. The other 8 beams, 1 to 8, use a dedicated fiber system. They don't go through the regular GBT IF system, so you cannot connect those to the DCR. Those can only be connected to Vegas. So all of them are connected to Vegas. And there is a little other thing when they were putting it together. Matt noticed that beam 8 didn't really have very good sideband rejection, but at that time we didn't open up the instrument to try to rectify that because we could have caused potentially more harm than good. So we didn't want to do that. So that only comes into play if you're mapping like 12 CO. You'll notice that beam 8 will have a much higher noise because it basically it doesn't have the sideband rejection. And there it's important to observe in the upper sideband, because if you observe in the lower sideband, the upper sideband would be sitting on the oxygen line and that noise would go way up for beam 8. Just lab performance, it performed as expected, basically, based on the measurements back. They had measurements in Stanford, they moved it to Green Bank and put it together. And anyway, it performed in the lab as expected, and this is performance on the sky, basically. So this is due to the atmosphere shooting up. Your system temperature shoot up here. And in the low end of the band, it's optimized really for around 100 gigahertz. They ideally, we targeted the 90 gigahertz for the dense gas tracers, as well as doing 110 basically. The receiver noise itself is really good, even up at 115, but that's where we hit the atmosphere. So Argus specific observing information. There are no noise diodes. I mentioned that already. And it's best to observe frequencies together due to the YIG. It takes a couple minutes to stabilize. If you observe and you jump from one frequency to the other frequency and you get an abort because it'll say no YIG, LO power, you just resubmit the script. It'll be fine after a few minutes. I already mentioned about beam 8 and the IF rack. The auto procedures, when you run the auto procedures like auto peak focus, or auto peak, auto focus, auto OOF, by default, they run the vein cal observation. So you can use that for calibration in principle. If you're trying to point and you're trying to save time and you don't need to calibrate the data, there's a keyword in here. You can turn that off. You can also change the order in which you do pointing and focus. You could do that for all receivers now. This is more important sometimes for Argus, in the sense that the elevation offset tends to be from night to night. It could vary significantly. So if you did the as pointing first, you'll miss the source because it's off in elevation. So you can actually do the elevation pointing scans first, and it can be a little more efficient. If you've been taking data recently this year, you would notice the as offsets are off a lot. And that's because we need to update the pointing model. We've done a lot of work in the last year in terms of, we replaced the as encoder due to a lightning strike in the summer, but it's been running, our as offsets have been running a little high, and I need to update the pointing model. You can do that with other frequencies too, but an example, this is all posted on the web page. You can download it from that Argus web page. So an example here is to do a peak. It picks your frequency. Thing you may not realize, when you do the auto, it picks a default frequency in the band. This is true for all receivers. For Argus, the default frequency is 86 gigahertz. Let's say you're observing up at 90 gigahertz and you want to use the peak scans for calibration, then I would actually put your frequency, at your observing frequency for calibration. But anyway, this just shows you an example syntax that you could call that auto peak command. That you set the frequency. This cal sequence will default true. You'll normally run the vein. This as L order actually defaults to false. See, but if you want to do the elevation peak scans first, you can set that to true. In general, we should always run auto OOF with the defaults with the calibration, because it's actually trying to do what it's doing, the processing. It's better for it to actually have that relative feeds calibrated when it does its processing. And the advantage of running that, it's the first thing you do. You can see if the instrument's actually working before you take a 30-minute auto OOF observation. So anyway, preparing for observations, just like everything else, you have to make the config files, your catalogs, observing scripts. The one difference, though, is you need to pick what source you're going to do to use the OOF. You just can't just say oof, and then just have it go to some random source on the sky, like some people do for pointing and focus as well. In the past, what I've done, I always go to the ALMA calibrator source catalog because they observe lots of things. This worked really well until around March 2020 when COVID shut everything down. So now ALMA's not observing that much. So you can still use their database to get historical measurements. You just won't have any measurements recent from ALMA. The SMA observes. You can get information from the SMA when Karma was around, or the Owens Valley Array before. They had a nice database you could get information from. The 30-meter you can have information from. We don't observe often enough in the 3 millimeters band to track all the 3 millimeter source to track their calibration. So I really lean on other observatories and their calibration, and I tie it to that. And ALMA is really good to tie it. Since we don't have ALMA now, we generally what groups will do is the recommended procedures: go observe a planet where you have the absolute calibration and cross-calibrate that planet with some other source that you're using at that particular time for calibration. The specific configuration parameters for Argus, this is an observing guide. The big difference here, I guess, you pick the sideband, lower sideband and upper sideband, only Argus can you choose that on the GBT. And then you basically, there's no noise diode. So if you're doing a position switching type thing, it's total power, no cal, or if you're doing frequency switching, switch power, no cal. Another thing, we only have one polarization. We have a single linear polarization for Argus for all 16 beams. So that decision was made, instead of having 8 dual beam feeds, it made more sense for mapping to have 16 single polarization feeds. But here's an example config file. I don't want to necessarily go into all this kind of stuff. We've recommended observing procedures. Natalie went over a lot of this stuff in terms of setting, doing relaxed heuristics. We do have a startup script, which you can get from that area, from the web, not from the web, but from the home Astro Util area. We start with an auto OOF to set the surface, and we do the brightest point source on the sky between, that's up above 25 degrees and not in the keyhole, in between 80. So literally the brightest available point source. So that's 3C84, 3C454.3, 3C273, 3C274 are the best ones right now in 2021. And there's a few others that are coming up that we can use maybe in coming years. But if the Ka band receivers on the telescope, it's at a lower frequency, the sources are much brighter, you're not as dependent on the wind, because when you have wind during an auto OOF, the Argus beam is very small, it can blow around, and then you can get bad OOF solutions. So sometimes if the weather is not really perfect, you can the OOF solutions with Argus can not be very good, and you're better not using those surface corrections, which usually will cause a hit in aperture efficiency for point source of 20 to 30% typically over than normal in comparison to when you have the OOF. So what I recommend is always using the Ka band plus the CCB for auto OOF when it's up there on the telescope. Unfortunately, right now it's not. It's much higher signal noise because it has a back end design to remove the 1/F noise, the Caltech continuum back in, and the sources are brighter. The beam is bigger, so it's not affected by the winds. We can show some comparison of Ka versus Argus OOFing further down in this presentation. Typically when I run, instead of running auto peak focus, I guess a lot of people probably, that's typically what our procedure works, because the procedures are written, they're very success oriented. But for Argus, I have a script auto peak, and then there's a break in it. So it gives you an opportunity to update the pointing solutions before you can continue with focusing, because there's no reason to focus if you're not on source. And an important aspect you can do, a lot of people, if you do not have a bright 3 millimeter source within 20 degrees of your target or so. You'll want to consider just pointing at X band or K band. And you can use the pointing and focus corrections for X and K are equivalent to the Argus one. So you could basically use a lower frequency receiver to get the corrections on the telescope for pointing and focus. And even though you lose a little bit of time with switching receivers, you gain that because you never have to repeat an X band pointing and focus. It's always basically clean, where for Argus, if you're off a little bit, then you have to do it a couple times. And sometimes you lose the sources basically, or people could lose track of the sources because they don't point often enough. So when they come back after, if they wait too long, the pointing has drifted so far and they can't even find their source with Argus. Lots of sessions early on that were lost because people go, oh, yeah, the pointing's not working. They can't find their source. So it's just, you can always go to a lower frequency, get the pointing corrections back again. And a lot of people now just point and focus with X-band. And X-band's nice in the sense it's right next to Argus in the turret, so it doesn't take very long for the hardware to switch receivers, basically. The operator can do that pretty quick. Since there are no noise diodes, anytime you take target observations or calibration observations for which you want to use that data and have it calibrated on an accurate TA star scale, you need to run a VaneCal script. There's an Argus VaneCal script. And then you can look at the results in Gbt Idl by just typing VaneCal and giving it a scan name, basically. And for absolute calibration, I have a little script called auto peak calibrate. So the idea here would be you have to do your auto OOF, you peak and focus, you have your surface, your pointing, your focus corrections. You run this just peak scan. So you scan across the source and as, N and L, and you can use that to drive the calibration of the telescope. The peak of those scans basically give you the aperture efficiency. And if you integrate over the curve, you basically get T main beam for a point source. So it's a quick and easy way to do it. A lot of times the other frequencies, people will do nods or on-offs using Vegas. The problem with the higher frequency is the underlying sky is changing so much. So when you're doing on-offs every 30 seconds, you can have the sky changing by a few Kelvin in those 30 seconds, such that your calibration can be off, because most of our sources are pretty faint. So your sources themselves are only, let's say they're 5 Kelvin, and then you do an on-off, and then you have that bouncing around by several Kelvin. In fact, you can bounce around even by quite a bit. So people do calibration and say, my calibration's negative. No, it's not negative. It's just the sky came into your off and it was brighter than your source. But when you scan over a source, you can take the time baseline, underlying baseline off, and that will produce more accurate calibration in general. Okay, this is sort of the obvious. You must maintain good telescope corrections when you're working at high frequency, pointing, focus, and surface. So in general, when you write an observing proposal, your science time, you actually ask for twice as much time as your observing time to take care of these corrections. And you shouldn't shortchange yourself on these corrections unless you're doing really extended sources and you don't really care about your beam, because too many people try to skip and cut corners on those corrections. But if you're not pointed and you're not focused, you're not getting quality data. And we should point and focus every 30 to 50 minutes at night, which takes 5 minutes. Auto OOF, you don't have to do that very often, as long as you have a nighttime from 10 p.m. to 6 a.m. You can use a similar OOF for the entire night, unless I guess if there's a huge temperature change during that nighttime session, then you might want to OOF again. And we already mentioned this before, the daytime, we don't recommend OOFing because it takes too long, and we're hoping Lassie can help out there. And then I have slides that, no, actually, Natalie already have taken these slides and shown you on what was it, day one? Yeah, day one. So I'm not going to go through here some example OOFs, good OOFs, bad OOFs. The main thing is you want to have a lot of good signal and noise in out of focus scans. And if if you looked at the data that we looked last night, the people that were involved in that wasn't the case. You want your beams to be relatively circular. There's a bad oof in windy conditions. Marginal signal to noise that still produced a decent oof selection. So even though this looks sort of dicey, it was, it's sort of marginal. But what I did want to show you is an example, same source, basically. This might have been even in the same session. I forget. It might be two different nights. It doesn't matter. Where the left shows the Ka band signal to noise for the oof, and and the right shows the, well, that's the beam. So it's actually, here's the comparison. So that's the Ka. This is just the Ka oof. And here's a comparison of the Ka to the left and Argus to the right. And this is on 3C84. This is the brightest, or the second brightest right now, point source on the sky in the northern sky anyway. And we got decent signal noise here, but look what we get with the Ka band. There's no comparison. So you can oof a huge number of extra sources with Ka band. So you can always get a good Ka band source to oof on. Whereas Argus, like I said, there's about 5 sources now you can use. And that's it. And there are certain LST ranges where it's a bit challenging. If this source is in the keyhole, if 3C84 is in the keyhole, it's 4 hours. There's nothing else until 12 hours or 16 hours, or actually to use. Okay. We recommend you can point and focus with Argus, but if in doubt, use the lower frequency band. Relax heuristics. I'm not going to go through funny example. Well, sometimes you need to look at the pointing data. You just can't blindly let that run in the background and let the telescope accept solutions. These are examples of good points. There are ways you can step through the pointing options, and you can actually send corrections and enter the corrections and send them to the telescope. We did that on our first night, because actually that was K-band, and there was issue with one of the polarizations that caused funny results. These are example pointings, good. You'll see this. Don't freak out if you see this a lot of times. We have this like servo jitter systems. And you don't see it really too much with the lower frequencies. The red is the data. That doesn't represent the actual beam of the telescope. That's just the system, the servo is moving around, the telescope shaking a little bit, hasn't stabilized, and you'll get these resonance every so often, and you'll see that. But this can affect your pointing solutions. Like it'd be a little so the data will try to fit a Gaussian to that jitter. And usually it gets the center okay, but be wary of that. Here's an example where the sky was changing a whole lot, and so it's trying to fit these Gaussians. So it tries to fit a double Gaussian in azimuth, and so there's this fat Gaussian here. But so our processing can do really funny things. This is an example where you wouldn't want to blindly fit the solution. Here it determined an as Gaussian over here. There's nothing there. We were off in elevation, so we didn't see it in as. And then in elevation, our brilliant software, instead of fitting this peak here, for some reason decided it was going to fit the peak here. So that's its solution. I don't know if you can see the little green bump down here. That's crazy. So how do you get around this? Even if you're not getting fits, you can put the cursor over the peak yourself. You put the cursor over the peak here. It gives you the X value, 0.28. So in this particular case, it looks like crap, except you see the source, but it was trying to give you an elevation correction of near 0 when it was actually at 0.28. So you can manually put in this correction of 0.28 by using this tab here. And then you can point and focus. So, or, yep.
Could you just scroll back up to the table, just in any image that has the table of results?
Table of results.
That Astrid gives you.
Yep, that's right.
Go up another slide, maybe. There, right there.
That's
so
right.
Can you tell us, just explain to everyone what of those numbers are important and which aren't? Because I still get confused by these.
Oh, okay. The top ones don't worry about. So what is in the system, the old as, I don't know if I can zoom in anymore. Can people see that?
I can see it.
Okay. Shoot, I clicked on something and now I have a spinning ball of death. But anyway, the current corrections in the telescope when you start are these old as and old L.
Mhm.
Those are what's in the system now, the telescope as PCs. So then you point, and then you get these delta as and delta L's from the pointing, and that can be those center values. Like that's when you get the center value, it's reporting that is what it averages to get the center. So you get two. Let's find a good one.
Mhm.
Let's go here. So we actually have the peaks, some good ones, not the bad ones. So in this particular case, we started with a 0 and an old as a offset of 0.35, and they pointed, and the center here was 0.159 and 0.146, so that's roughly about 0.15. So the system derived a 0.153 by averaging 0.1459 plus 0.146, and that was a new delta. That's a delta Z, and applied the delta Z to the current LPC, which in this case was 0, so it just added 0.153. In elevation, it was the center was pretty close to 0, is 0.026, and this is 0.014. It averages those to get 0.02, so it added 0.02 to 0.35 to get 0.37. And then these are the new LPCs.
That's what you'd put into the send corrections box.
That's right. That's what you would put in manually, or if you have to put your cursor on yourself, like on something like this, since you have this jitter here, I would ignore this 0.041 and just use the 0.16. 16. The system, what it would do here, what I didn't have
And
to
the
understand, knows.
P-as, you say don't worry about that, but is that to do with the underlying pointing track model?
I'm sorry, I missed.
I was just curious. I mean, you said not to worry about what the P-as and the T-as.
Oh,
but I was just curious. Are they just the track model corrections or something?
that might be. Oh, I would have to look in the headers on that. Actually, I don't. I need to do. I would have to do. Those might be the dynamic corrections that are going.
No, I was just curious.
I think those are the dynamic corrections that are going on, but I'd have to go looking at that.
Thanks.
But yeah, it's below the dotted line. Where you can use as the information. So yeah. Okay. So the new LPC is equal to the old LPC plus whatever that X value is on that graph, or it reports it as a center value here. Okay. So here's an example of the same source on the night where the observer was having a hard time pointing here. They couldn't really see the source. This is actually a relatively bright source. They shouldn't have been observing with Argus, but they get scheduled, and sometimes you'll get scheduled in sort of crummy weather. So then they switch to X-band, and you can see, not to belabor the point, X-band pointing, it's easier to see the green fits to the data. You can't even see the data there because the red line data lines are underneath it. There is no noise in comparison, where in Argus, it's just a little dicey. You wouldn't want to trust that fit or that fit, obviously. I mean, here, heck, it was trying to fit something way over here. It doesn't know. Anyway, there are ways to monitor Argus in the logs. We do have a Clio window. I'll just leave this. There are actually manager logs and sampler logs, more information that people would know what to do with. So I won't go into that. It's in the presentation. If something happens, we need to figure out what went wrong. We can go through some of the history and figure it out. But those are some of that is hard to figure out in real time. The real-time system will throw an error if there's no LO power. So here's an Argus Clio window. Looks a little different now. Dane had switched it up a bit. But anyway, you can look at the Bain state, which is OBS, means you're looking at the sky versus Cal, when you're looking at the vein. There's this angle changes with whether you're obs or cal. So sometimes it'll get stuck at a funny angle. In the past, when it was really cold, it wouldn't work very well. There's a little heater in there now, so we're hoping that mitigates that. If you need to turn the manager on and off, you can do it under this tab, the manager tab. The operators will sometimes complain that there's all these error messages there you can get, and the error messages won't clear themselves up by themselves as one would hope they would sometimes. So you can turn the manager on and off and get rid of them. And you have to unclick this button here, the lock button. And sort of funny, it's locked and they give a green symbol, and when it's unlocked, it's red, but you can't do anything when it's green. Things to watch out for, the instrument has to be on. So when you do the startup script, it actually checks and see if the instrument's on or not. If it's not on, it turns it on. And then it issues the default bias values of the instrument. So if you do have this window and you're observing, you need the LO power, the instrument has to be on. If the instrument's on, channels 1 to 8, which are the dedicated fiber system, they run at a higher total power, about 1.2. When you have good LO power and everything's, the levels are set up right. The other ones, 9 through 16, that go through our IF system, they run at a lower level. But it should be about 0.8 when they're good. But anyway, those are some things to look at. You get experience. We have these buttons here that are green. Sometimes it won't look green, but don't freak out if it's not green. The conversion of whether it's good or bad, it's a little bit fuzzy, and we're still working on that. I'm not sure if I can fix that. We lost our manager person who wrote the manager, so it's hard to make updates to the software on that. But sometimes that'll be in yellow, like you'll see it in yellow. But if you configure and stuff, it should be, generally you should be in green, but I would check the data and make a note in your log if it's not green. And then if there's some question about that, you can ask your friend or ask me, and I'll look in to see what happened during your run. This has been shown before, but just on the status window, I'm always looking at the status window when you're doing high frequency. You want to make sure the LPCs you get from your scans show up. And after the OOF, you want to make sure this little green number dot turns on. It means it took your thermal corrections. And your Vegas value should always be about -20 for all the ones you're using. So you can see everything right in one page. I actually like this page for that purpose. And you can see what the winds are doing, but anyway. Balancing, I already said this, the Vegas is -20. The IF rack values for Argus are 1.5, and that shows up on the OD1 to 8 values. This is just documentation, but let's say you have an issue with some part of the system. Let's say converter module 6 has an error, and you go, what's going on with converter module 6? I don't know. How does that affect me? Well, converter module 6 corresponds to Vegas bank B2, and it corresponds to Argus being 12. So this is just a mapping of where which part of the Argus, which Argus beam goes through which part of the our system and is attached to which Vegas bank. So if you have issues with balancing, one of the Vegas banks could be off, and then you could actually correlate that with the Argus beam. And that the dedicated fibers, we used to have a lot of issues with that. Steve White, our engineer, has fixed those. So right now we have all good 16 beams. We hadn't had that for about 18 months, which is, it's nice to get that taken care of. We have YIG power. You don't have to worry about this as long as you have some YIG power, but this is sort of what you would expect to see roughly, the YIG power versus frequency. If you go down, we're basically run out of LO power if you get down at the low end of the band. This is very marginal. So we can go down to 75, but 80 is better. You can go down, you can do the 77 gigahertz line, for example, but it's tough to go. Well, you can't go below 75. Troubleshooting, basically you need to make sure obviously the instrument's on, run the startup script. The vane can sometimes get stuck in very, very cold conditions. Hopefully that won't be the case, but you can check and see where the vane's pointing. Because if the vane gets stuck when you do the TSYS, it'll be doing, you know, the vane being on, it'd be doing vane minus vane divided by vane calibration. You'll get really bogus system temperatures. You need to make sure there's LO power going to the YIG. You don't necessarily need to watch it. If there isn't sufficient LO power at the beginning of your scan, you will get an abort. So when you get aborts with Argus, this is one of the leading causes of those aborts, especially right at the beginning of the first Argus observations, or if you switch from doing whatever 12 CO down to HCN, you switch a huge range. You just go. That can come into play when you're pointing in focus. If you use the default pointing in focus is at 86 gigahertz, and then you keep observing up at 110 gigahertz. When you go back and forth between that, you can have error message with that has no LO power. The way around that is just reissue the script or change your pointing frequency to match your observing frequency. Argus's fault. Sometimes you get in a fault state. So if you get in a fault state, let's say it aborts and you're in a fault state, you don't know what the heck is going on. You can reissue the script, the configuration script, and if that doesn't seem to work, you can turn the manager off and back on again and reconfigure and see if that clears it. If that doesn't work, it doesn't always mean that Argus is a problem. It could be another problem, and the operator might be able to help you with that. And if it's on the software side, they can restart Turtle and then you can reconfigure. And if you're still all stuck, then you basically call the on-call support expert, which I guess can be Larry, Will, and I now, maybe. Anyway, calibration, we have one load, the TA star. I don't want to go through all this. This is in that memo, but I do want to mention the temperature scales are vastly different. At lower frequency, they're not, but at a higher frequency, they are. It's just a use case here where TA, the antenna would be 100 millikelvin. Your TA star would be 580 millikelvin, and your T main beam would be 2.3 Kelvin. So sometimes people, when they write proposals, they just say, we observe to some Kelvin, but they don't give the scale they need. So the amount of time to observe to 100 millikelvin versus 2.3 Kelvin to 3 sigma is a huge difference. And we've had even internal staff members who will remain nameless put in proposals that would be off by a factor of 500 in their requested time. So just watch out for that. There's some scripts. Point back to the memo. Now we'll go just really quickly a little bit into sort of how we do things with the Argus data. Processing, and we have our raw data that comes in, it's stored in the GBT data, and we have our raw Vegas data, and this is true for all receivers. We have the online filler that makes the SD fits file, and that's in /home SD fits. That's what you were working on with Gbt Idl. And then what we do is we write scripts. I have scripts that can and that convert to go from SD fits data to calibrated, call it keep data. So I loop through the data and I save the calibrated data as a keep file. And then we use the gritter to map it in step 3 to produce your data cubes. So these are tables, basically, big flat tables. These are calibrated tables that you can look at the spectra within Gbt Idl. There are other tools out there that can handle SD fits files, but generally we use Gbt Idl when we're working with the SD fits files. For now, anyway, people are talking about converting it over to Python version. And then we use the gritter to make your data cubes, and then you can use your DS9 or your CASA. And Larry went over some of this stuff, just sort of the Linux environment in the early day, but just as a reminder, your home area, you have a scratch area, your home area has a quota. We store data by project under home GBT data. The Vegas data is stored here under Luster, GBT data under the project name. Your SD fits file is stored under home SD fits. And our data processing machine, this is so example on how to use a Gbt Idl. This is just basic overview. So here, but I can quickly mention our scripts that, so Argus scripts are located there. The vane cal reduces the vane calibration observations and provides the thesis for all the beams. The get atmosphere goes into Ron's weather database. It's an IDL script that spawns off some shell scripts that Ron has, and returns the information in an IDL way, so you can use it within your Gbt IDL scripts. I use it within the VaneCal script, and I use it within these scripts here. So I have a simple script here to do frequency switching data for individual scans, and then another script to do the total power on-off scans. And then there's a whole bunch of different other scripts I have for mapping, depending on what they're doing. I don't have I should put generic mapping scans in there, but I'll do that actually. I can have some generic ones. So this just shows the example running VaneCal 19, and it spits out the system temperature for all 16 beams. It looks a little different now because I have feed number and beam number, but anyway, it returns the zenith opacity. And in this particular day, it was pretty good where we're at 89 gigahertz. So we're doing like HCO plus, and that tau was 0.075, which is pretty good. That TSYS due to the atmosphere, not including the microwave background, was only 26 Kelvin. So the rest of it spillover and other microwave background and the actual receiver noise. And anyway, so that tells you, you can check your quality of data and then do a quick look. Here's an example of a frequency switching where you just give it a scan, and that's the vane calibration. And this is one of the beams. Feed number 9 is beam number 10. That's what we use for pointing. They were, I forget, this is one of these Perseus clouds that Shea Storm did, and this turned into a large project that's on the telescope now, DISCOS, that study the dynamics of star forming cores. Mapping commands, people in my group, we got to see this a little bit. You can run, after you calibrate the data, you can run the gridder. You pick the number of channels on which you're going to want to grid over or map over. This is A is averaging. Since I take the baseline out and stuff, I don't even make a line or a continuum cube. It'll just output a cube file. And I think that's all I had here in terms of this presentation of material. So what time is it? Yeah, whatever. I've probably talked long enough. So if people, the bottom line is you can observe with Argus, it works well when things are working, but we're very weather dependent, and you need to be very careful in terms of getting the telescope corrections in place before you observe. It's much different than the lower frequency, like pulsar people, H1 people. They don't actually they don't need to think very much about what's going on with the telescope. They can just issue the scripts and concentrate on like the data, the science data coming out. At higher frequency, while you're observing, you should be looking at the state of the telescope. Do we trust that pointing correction? Is that focus correction makes sense? What are the surface corrections? Because if you don't, your science data will be impacted. And so, so it's a different mindset, basically. Some people catch on and do very well. And to be honest, some people actually struggle. And it's independent of certain background too, I found over the years. But anyway, just recommend being careful. If you don't understand something here at higher frequency, you need to actually ask the questions so you get a good feeling. Because I think that might be some of the problems. People get caught up in information overload, and they're afraid to ask. They don't ask the questions, and they just assume. You can't assume, well, the system's going to do the right thing. You get away with that at low frequency, but not at high frequency. So that might be the bottom line in terms of how you observe approach observing it at the highest frequencies with the GBT, because we are pushing the limit. I mean, it's a 100-meter class telescope in the open air, steel backup structure. And it's actually pretty amazing that you could actually get a surface down to like a couple hundred microns, actually. That's really, truly remarkable. But we have to work to get it there. It doesn't come for free, and there's a lot of overhead involved to get good science data out. So that's the downside. And you'll be scheduled in pretty marginal weather most of the time, because that's how the DSS works. Because if the weather's really, really good, Mustang will get the weather. So you get second-tiered weather as being Argus. Okay, do we have any? I'm going to stop the share. And do we have any questions? And we retained some of you. Thank you to the 17 dedicated people that hung on. And okay.
I have a question. So maybe a way too long question, since I see we're already at time, but I was wondering if you could say something about W-band. And
Yep.
that I'm probably one of the few people actually using W-band, but
W-band's awesome. It works at the very low frequencies if you want to do deuterated lines. We had Scott Snave that had this beautiful project, who's making big progress, and he left the field and nobody actually picked it up. So it has a web page too. If you hit, instead of typing Argus, you can put, whoops, I'm not showing this now. I should share it. You type 4 millimeter. Let's see, I can share screen again. Let's see. Now, can you see this web page? I'm moving around. So it has its own web page. Be honest, I haven't updated it in a long, long time, but it's similar in the sense of the corrections are the same way. The difference is it actually has a hot and cold load. So we actually do a dual load for calibration. It's sort of cute. Let's see, do I have a how to observe with 4 millimeters? I haven't opened this up in probably 5 to 6 years. So let's see what we have here. I commissioned it in 2012. It looks like this is the 2 feeds, and then the cold load's in between. So there's a mirror, and it looks back down in the cryostat. But anyway, blah, blah, blah. Has information for proposals, similar sort of stuff. The vein, instead of, we call it a vein cal for Argus, it's called CalSeek for the 4 millimeter receiver. And it's sort of a similar sort of deal, but one of the differences, it does have both polarizations. It's 2 feeds. There's still no noise diodes, so you have to write your own reduction scripts. And I have a set of reduction scripts for the 4 millimeter observer. I think I have reduction scripts there. If you need reduction scripts, come to me. It's been a while. Oh yeah, I have it in the same area here. Under Home Astro Util Projects, it's under 4 millimeter Pro. So Argus is under Argus and Pro. But I haven't gone into that. And to be honest, in the last five years, we haven't had anybody really use the 4 millimeter for spectroscopy. It's used for VLBI observations. So here's a picture of the wheel, and uncovered. And here's sort of the picture and what it looks like. And it can rotate around, and you can put, so the cold load's in the middle. But what happens is, so you can look at both beams on the sky at this position 0 with both beams are seeing the sky. Then if you move cold 1 onto beam 1, then the warm load is basically over beam 2. So we have a warm load, and then this over here on the cold load is actually, it's a mirror, and the mirror reflects back. You can't see this other mirror, and then it goes down in the middle to look at the cold load. So the cold load itself is very cold, but the effective temperature of the cold load through the optics of this thing, so it's cold underneath here. Here's a feed, here's the 2 feeds. So you can see the radome, the white. And then, so you can basically, when one beam's looking at the cold load, the other beam's looking at the warm load, and vice versa. So when you do these cal sequence scans like before point focus, it'll look like this. you see the sky, then this beam 1 sees the cold load, beam 2 sees the warm load, then it goes back and forth. This is when it's rotating around, it sees the metal of the wheel, and then it gets the warm 1, and then cold 2. But anyway, so that's how it does its calibration. It has a better Clio page in the sense that it has feedbacks. But in terms of observing, it's the same deal in terms of the auto OOF, how often you need to auto OOF, quasars, go through some of the OOF there. I would still use KA band if possible, but if you're using W band and W band's up, go ahead and you can do W band to OOF on instead of Argus, so you just have it in the system. They're basically have similar systems to noise. Actually, there's advantage in the 4mm receiver W band. It works at lower frequencies at 77 gigahertz. It's the default frequency. So the beam's a little bit bigger than the Argus beam at 86 gigahertz. Well, that has some advantages when you're trying to point and focus. And we have the same issues. And actually you can see these plots are almost the same because, but anyway, on the status window. So the optical, so that's Vegas, and then that's the optical drivers. Okay. And then I have receiver checkouts, and then I have scripts. So like Argus, I have Argus scripts. I have a W nod script. I have a W on off script, a W frequencies. Oh, I guess on off gain. Anyway, I have the similar sets of scripts there, and it's the only difference in applying the calibration. As the 2 loads, it does a direct calibration. And it puts it on a TA scale, not TA star. So the default temperature scale you get from running my scripts are basically on TA, and then you would have to correct for the atmosphere. Or you could rewrite things and use just the warm load, which I've done for some people. Okay, sorry. So that's a similar sort of thing. You can go to this page. It's broken up into bands, basically. They have tunable frequency range, but I won't go into it. It goes through a millimeter converter rack. So you can do, typically you can do 4 gigahertz at a time, basically have access to 4 gigahertz of instantaneous bandwidth, except at the low end of the band. You actually have access to 6 gigahertz of instantaneous bandwidth, where Argus, you only have 1.5 gigahertz of instantaneous bandwidth. So if you're trying to do deep observations of a core targeted, you don't want to map, and you're like doing a deuterated species or something at the low end of the band, I would use the 4mm receiver if you're just doing a deep spectrum. But if you're trying to map something and they're brighter lines, yeah, I would use Argus. Argus works, the 4mm receiver, although it says it works up to 93, above 90 gigahertz, I would not use the 4mm receiver now. It's optimized for the lower end of the band. So 75, 77, 72, it's awesome, basically. I mean, we get really good performance down there in terms of the LNAs were optimized for the low end of the band, where Argus is more optimized for the high end of the band to get the CO as well.
Thank you.
But yeah, question, do you have an active 4mm project?
Yeah, I do. Yeah.
Is Larry your friend on that one, or is this the one?
Yeah, Larry is my friend on that one.
Okay.
And we've been going over scripts and things already and trying to get everything set up. Yeah.
If you run an auto calseek command, put 45 seconds in instead of 30 seconds if you copied something from somewhere else. Okay,
Sorry?
we can take that offline.
Yeah. Yeah.
We'll take that offline. The wheel is running slower than it normally, like how it used to run 5 years ago. So I
know about that, so yeah, I'm aware of that.
okay. The workaround is just to put 45 seconds in for the calseek commands instead of 30 seconds. And it'll work okay. It should work okay. And if we have issues with it, we might have to run with the manual calseek commands. But anyway, we'll take that offline. Okay. So that was, hey, that chased more people away. We have some diehards here that are still staying on. So does anybody else have a question?
Just a comment from Chintel that he also has a W-band project for
Okay.
high redshift line detections. Jim is working with him on that.
Okay. I'm hoping, yeah. So that's up for, I'm not sure how long that's up for. So before they remove it, so so there we have a receiver schedule. Let's see what Tony's thinking. Up through February into the early March. So according to
up again.
Tony's master plan schedule. What? I'm sorry?
I believe it'll also be back up again in April.
Yeah. But in the April run, it's up there for a little bit, and that'll be used for VLB observations. That's right. So back up in April. So if if you can't get your observations in and your source is still visible in April, we can get there. So we need to get, after the snowstorm goes through, we need to start observing with W band. So you're doing targeted observations, both the W, is that correct? Or are you trying to map?
No, I do deep spectra for a couple sources. Yeah.
Okay.
Meryl's actually scheduled last Sunday, just a few
Oh,
days ago, but then
okay.
the snow came through again, and that combined with the wheel.
Yeah, I'm glad that didn't happen because I was away and I saw that and I go, shoot. And I looked at the data that Bren took and I'm going, uh-oh, the wheel isn't operating right. I don't know what's going on. We've had some issues with the wheel. They have to spray a Teflon. Well, anyway, usually they clean it up and it works for about when we were using it a lot, half the year, and then it would start to gum up and then stick. So I don't think it's sticking. It seemed to move pretty smoothly. It was just moving slower. So I don't know. I need to talk to the engineer. This is a problem with COVID. You can't have these casual conversations. The engineer, they might have changed the motor out on that. A year ago, not a year ago, a couple of years ago, they had issues with one of the sensors, and I think he redesigned it a little bit. So I think he might have put a more powerful motor, but a slower motor in there. And that wasn't communicated across the observatory. I think that's what happened. So I think it just moves slower now. So we updated the software config files to make it work with the current hardware. So I think we're okay now. But I'm glad you weren't scheduled on Sunday because I wasn't available to help. And that could have been interesting. So that was a blessing in disguise. You don't need to be abused that much on your first observing run on the telescope. There'll be plenty of chances to be abused later for other issues. Okay. And okay, we have one other outside person, and I don't know your name. I can't see your, I think. Let's see here. Oh no, we have a few. Sorry. Oh, more. The way the Zoom was looking, I thought we only had a couple people left. I'm gonna stop my sharing. I can't actually see everybody. Now I can see everybody. We have 14 people still here. It looked like we had lost, when I started sharing and going over 4mm, it looked like we lost everybody, but.
We're in dump ship.
Okay. Do we have any more questions? It can be general questions over anything you want to bring up on the workshop, not just Argus or W-band. We're available for email questions. We have the help desk as well you can submit. So generally when you have a project, you get assigned a friend and you have somebody to contact directly to start with, but you could always submit a help desk, and you can submit questions too to the individual staff now that you know sort of who knows, experts on different areas or whatever, or somebody that you worked with, through the workshop. Feel free to send them direct email questions, even if you don't have a project. Okay, well, I'm going to hand it back if you want to say anything else.
The only thing I have to say is thank you, Dave.
Okay.
And everything that Dave said about contacting your project friend or submitting a help desk ticket is true. Don't hesitate to reach out if you're having any problems.
And if you're trying to contact me, you can send me multiple emails. I miss emails, unfortunately. I get too many of them. As Will is smiling. He knows that to be the case. I didn't read 7,000 emails in 2020. I set a new record.
Oh, wow. So help desk, if you're trying to get a hold of Dave, might be better.
No, I do the emails. Subject lines are very important. A blank subject line with RE is not going to get looked at. Or a statement, dear all. I stop reading after that. But I say, Dave, help me now. I will try to respond quickly. Okay.
Alrighty, I think we're about finished. The bulk of this talk will also be available if you want to review anything that Dave has said.
Yeah. Oh, it's recorded.